everyone, and welcome to Bash Course Quarantine Chemistry. My name is Faith, and today we're going to learn about kinetics. So, kinetics is the study of rates of reactions, and reaction rate is measured in molarity per second. Rate expressions are often written to show how chemical reactions occur. These can look like delta products over delta T, or negative delta reactants over delta T. For a given reaction, you can relate the rate expressions for each. If the molecule is in the reactants, its rate will be negative, and for all molecules, its coefficient will become a fraction in front of its rate expression. Here are a couple of examples of rate expressions for a reaction. So we generally work with average rates because instantaneous rates are always changing. When writing rate expressions, coefficients become fractions, and reactants are negative. So this can be coupled with stoichiometry and laboratory observations of product formations, including UV-vis spectroscopy, conductivity, and pressure changes. The instantaneous rate of reaction can be determined using a rate law, which is written relating concentrations of reactions at certain time to the rate, which is expressed as rate equals K times the concentration of A to the X times the concentration of B to the Y. K is the rate constant, which has variable units and depends on the reaction. It is only impacted by temperature changes. When writing a rate law, only include the reactants. The exponents x and y are indicators of the reaction order, which is determined experimentally. It does not come directly from the coefficients of the reaction. If the concentration of a reactant changes, the proportion that the rate changes in response gives you the order for that reactant. If the reaction is zeroth order, K has units of molarity per second. If it's first order, it has units of 1 over seconds, and if it's second order, it has units of 1 over molarity times seconds. One strategy for analyzing experimental data to determine reaction order is called the method of initial rates. So let's work through an example to understand that. All right, so say we have this prompt and we want to determine the order of the reaction with respect to each reactant using simplified numbers. So we're given 3 trials, 1, 2, and 3, with 2 reactants, reactant A and reactant B, whose concentrations vary based on the trial. So in the first trial, reactant A has a concentration of 2 times 10 to the negative 2, then 4 times 10 to the negative 2, then 8 times 10 to the negative 2. Reactant B has a concentration of 1 times 10 to the negative 2, which remains the same for the second trial, and increases to 2 times 10 to the negative 2 for the third trial. The rate of the reaction is given to us for each of these trials and goes from 0.2 to 0.4 to 3.2. So to figure out this problem, we want to try to isolate the effects of changes in the concentration of one reactant. This means we want to look for 2 trials where one of the reactants remains constant. So in this case, reactant B stays the same from trial 1 to trial 2. So we look at reactant A and we see that it doubled. And then we look at the rate, and you can see that the rate doubled in response. This means that this reaction is first order with respect to reactant A. All right, now for B. Unfortunately, there is no trial where reactant A stays the same, but that's okay, we can deal with that. If we account for the effect of the change in A that would have had on the rate, then we can see if B had any additional effect on the rate. Okay, so from trial 2 to trial 3, reactant A doubled in concentration again. So that means the rate would have doubled to 0.8. However, the rate is actually 3.2, not 0.8. So this is another 4-fold change in the rate. Reactant B only doubled, however, from trial 2 to trial 3. Since reactant B doubled and the rate quadrupled in response, that means that this reaction is second order with respect to reactant B. This is because reactant B doubled, but the rate quadrupled. So the change in reactant B was squared to get the change in rate. And this exponent tells you that that is the order with respect to B. And that's all you have to do. Another way that we can look at rates of reactions are through integrated rate laws, which graph reactant concentrations over time. For each reactant order, there is a different integrated rate law. For a 0th order reaction, the rate law is the concentration of A at a certain time equals the concentration of A naught minus KT. For a first order reaction, the integrated rate law is the natural log of the concentration of A at a certain time T equals the natural log of the concentration of A naught minus KT. And for a second order reaction, the integrated rate law is 1 over the concentration of reactant A at a certain time t equals 1 over the concentration of reactant A naught plus KT. So graphs of these, unlike what we looked at in the method of initial rates, which gives you differential or instantaneous rates, can tell you what your value of K is. So if you have a 0th order reaction, you can graph the concentration of your reactant over time and find a straight line and find the slope of that line. That slope will be negative K because it'll give you a negative slope. For a first order reaction, you can do the same, except graph the natural log of concentration versus time. And for a second order reaction, you can graph 1 over the concentration versus time. However, for a second order graph, you have to be careful because the slope there is positive K, not negative K. So let's look at an example to get this straight. Let's say we have these graphs. What is the order of the reaction, and what is the value of K? Since the graph of the natural log of A versus time gives us the straight line, we know that the reaction is first order. So we find the slope as negative 2.6 minus negative 2.1 over 10 minus 5, which gives us negative 0.1. However, K is the negative of slope, so K equals 0.1, and since this is a first order reaction, the units are going to be 1 over seconds. Another concept we can talk about is half-life, which is the time it takes for half of the reactants to be used up. However, you only need to know how to solve this for first order reaction, for which it is half-life equals 0.693 over K. This is because for 0th and second order reactions, half-life is going to depend on your reactant concentration, which is beyond the scope of most high school courses. For first order reactions, it only depends on K, but if K changes due to a change in temperature, etc., half-life will change. The idea that makes kinetics possible is something called the collision theory, which describes the conditions necessary for a reaction to occur. Particles must collide, and they must collide with enough energy to overcome the activation energy of the reaction. They must also collide in the correct orientation. And changes to these factors are going to affect your rate. You can increase the rate of reaction by changing the number of effective collisions through several factors. Increasing temperature is going to increase your average kinetic energy, which is going to increase your molecular speed and thus increase your number of collisions. And then therefore, you're going to make it more likely that you're going to have a collision with high enough energy to overcome your activation energy. This increased Ke is also going to increase the energy of each particle, also increasing the likelihood that you're going to have a high energy collision. Increasing concentration will also increase collisions, as will increasing surface area. You can do this by breaking a reactant into pieces, because you're exposing more atoms for collisions. Catalysts can increase the rate by lowering the activation energy like so. Also, if you change the phase of your reactants to one with more motion, more collisions will result. Based on the collision theory, we can look more closely at how molecularly reactions happen. These are called mechanisms, which propose broken down steps in a reaction called elementary steps. This introduces the concept of an intermediate, a molecule that is formed as the result of one step, but is used immediately in another, so it doesn't appear in the overall equation or in the rate law. Elementary steps can be unimolecular, bimolecular, or termomolecular, with termomolecular steps not being as common as uni and bimolecular steps, though. This depends on how many reactants there are in each step. For the rate laws of elementary steps, the coefficients can become the exponents in the rate law. For every mechanism, there is a rate-limiting step, which determines the rate law of the overall reaction. It's also known as a slow step, because the reaction cannot proceed at a faster rate than its slowest elementary step. Multi-step mechanisms can be graphed on energy diagrams, with each transition state having its own peak. Comparing the activation energies of each step to each other, you can also determine what is the rate-limiting step. Let's do some practice with mechanisms now. Say we have this mechanism, and we're going to be asked to write the overall reaction and the overall rate law. So what's given to us is that step 1 of our mechanism is NO2 plus NO2 yields NO3 plus NO. And that is the slow step. Step 2 of our mechanism is NO3 plus CO yields NO2 plus CO2. And that's going to be our fast step. So, to find the overall equation, all we're going to do is add these steps together. That's going to give us NO2 plus NO2 plus NO3 plus CO yields NO3 plus NO plus NO2 plus CO2. So we can also see by looking at these reactions The NO3 is made here in the products of the first elementary step and then used again immediately as a reactant in the second elementary step. This is what we call an intermediate, and like we talked about before, intermediates are not going to show up in your overall equation or in your rate law. So we can cancel things that show up on both sides of this overall equation, which includes our intermediate NO3 and one of these NO2s. So that our overall equation is NO2 plus CO yields NO plus CO2. Now, for the rate law, you know that when you have a mechanism, the rate law comes from your slow elementary step, and it's only going to include the reactants. But because it's an elementary step, the coefficients of those reactants can become the exponents. So our rate law is going to be rate equals K times the concentration of NO2 squared, because that's your slow step, and you have two NO2s in the reactants. And that's all there is to it. All right, so we've been mentioning the term activation energy for a bit now, so we should clarify what it means. It is the minimum energy required for a chemical reaction to occur, which is determined by the potential energy level of the activated complex. Catalysts, as we've mentioned before, can increase the reaction rate by decreasing the activation energy. Acid-base catalysts can modify a reactant by giving it one more or one less proton. Surface catalysts can hold a reactant into one position, and enzymes can change the mechanism itself. So catalysts, though they can't be in the overall reaction, can be included in the overall rate law. When changing particle energies, etc., one good way to visualize molecular states is through Maxwell-Boltzmann distributions, which show the distribution of particle energies. You can tell how many particles will have energies higher than the activation energy. If temperature increases, the curve is going to flatten or shift right. The overall area is not going to change, but the proportion of molecules with a higher energy is going to increase. One last thing before we go, the Arrhenius equation. You won't have to do calculations with this, but you do need to understand its relationships. K equals AE to the negative E sub A over RT. So the rate constant K is related to A, the frequency factor, E sub A, the activation energy, R, the gas constant, and T, the temperature. In a graph of ln of K versus 1 over T, the slope of the line will be negative E sub A over R, which allows you to determine the activation energy if you get a straight line graph. If you do, we say that K obeys the Arrhenius equation. That's all of kinetics. Good luck on the test. Thank you all for watching Bash Course Quarantine Chemistry, and I'll see you again next time. The Bash Course Quarantine team is Sandro Ansari, Sam Mencimer, Eamon Cole, Pasha Ishaq, Sarah Orozco, and myself. Please put any questions you have about the video in the comments below, and we'll try to answer them or get Dr. T to. Remember to tune in next time on Bash Course Quarantined, and as they say in my hometown, oh my EOSH.